So I talked quite a bit about SQL injection attacks. Just backing up briefly, but without getting deeply into this, I should also note that, that there's many many ways to so many other variants of these kinds of attacks that that might not actually inject code, but just use flexibility in the types of values or the ranges of normally legitimate queries that users can access that can sometimes leak information. Now, this is a very simplistic example here where a database, database logic allows, doesn't allow you, ordinary users to say submit arbitrary queries, but does allow you to say, query, what's the average salary among a group of users, a large range of users, right? But that's still super potentially very dangerous if it turns out that there's some way to sculpt that query for to artificially restrict the scope of aggregation to a very small number or say a single user, a single target user. In this case, the CEO, for example. We'll get much more into that kind of question later when we talk about differential privacy and things like that. So I'll just briefly mention that going forward. So now that we've talked about remote attacks, let's talk about about ways that actual stored or on the wire data can be protected along these paths. Now, we briefly mentioned before. We talked about encryption in general last time and different types of encryption algorithms and the way they're used, the way public key and symmetric key algorithms are used. But there's basically two ways in general that encryption applies to databases. First of all, we generally want the data in motion to be encrypted, namely the data going, say, between a client and the web server, and sometimes we want data to be encrypted, say, between the web server application logic server and the SQL server. And so that's an example of data in motion. And for this, we usually use TLS. Now, TLS generally works. It's believed to be reasonably secure, at least as long as it's a recent, well validated version with a solid implementation. On the other hand, various aspects of it, like public key infrastructure, managing the certificates that used to authenticate the different parties in these systems, can still be problematic. Many companies run their own certificate authority that within the company that manages that hands out certificates and basically manages the identities of servers in the company. This can be another point of failure, right? So if the database is authenticating clients that are coming and trying to connect to the database through TLS via certificates that deployed by the company, but the company's local certificate authority is hacked or hackable in any way, then the attacker can perhaps impersonate an otherwise legitimate client in getting a connection to the database and getting into that encryption. So I won't get deep into the data in motion topic, but just kind of a reminder that getting stuff securely and privately to and from database servers is one important element. But a second, of course, is the security of the data at rest, the data as it's sitting on disk in the, on the actual database server, wherever it's located. And this is especially the kind of situation where, like I mentioned, it's not the most common case, but it certainly can and has happened that attackers have physically broken into the premises of a company and carried off servers, in part just to get the data on the hard drive of those disks. And sometimes if that disk has a giant unencrypted password database, then the attacker can really win. Yeah. Mm.
But if the server needs to be able to read and write data.
Absolutely. That's a big problem, isn't it? Yeah. So the server, somehow needs to be able to read and write the disk, so there needs to be a key for it somewhere, a symmetric key. And without getting into I'll get a little bit more into details in a minute. But how you manage that key and where that key goes, is one of the big security questions. If it's stored, if it's just on the same server, then physically carrying out the server, you'll carry out the key with it, right? So yeah, let's look briefly into several types ways to apply encryption at data at rest. There, as in most cases, there are many options. In some sense, the most general option is full disk encryption. So this basically operates very close to the block device layer, the disk driver level in the operating system, and basically encrypts every block of data that goes onto or comes off of a particular disk partition. And so it basically automatically encrypts everything that goes on and off. But you don't get to pick which parts of the system are encrypted or not encrypted. Often you don't really need to if encrypting everything is often just fine. But other approaches are to encrypt at the very top level, at the application level, encrypting data before you even send it to the database, and decrypting it when you come back to the database, so that the database server never actually sees the clear text of the data. Now, this this is this can address the question you asked about. If we use full disk encryption, then of course every time the server boots up, it's got to have a way to recover the key to access the encryption. And if that key is stored on the thing, or if it's stored on a YubiKey inserted physically into the server, which is another way, then of course if the server and the key kind of get stolen together, you've still lost the data. On the other hand, if you can encrypt the data somewhere else on a different server before it even gets to the database, then that can be some defense against that, right? Then the attacker who takes the database server doesn't automatically get the key. But there are other and then there's encryption approaches that operate at the database level, where basically the database encrypts and decrypts records when they go on and off into and out of the database. I should have had a better slide about key management. So there are definitely more advanced ways to manage database keys. One of the and often what if you really want strong encryption, you really want to store the key elsewhere, and so sometimes you do that by having a network setup where when the database server reboots, it has to go talk to another server by a very carefully by a communication path very carefully controlled by the network environment to some kind of password server, a master database password server, and it kind of goes there just on boot up to get the full disk encryption key, unlock the disk and go with that. So, in principle, if an attacker comes in and picks up just the database server but doesn't, get the master, password server in this other room, they hopefully won't get access to the disk. But, that's not a perfect solution either. But, in general, key management is, in these kind of situations, is hard, and there are only trade-offs. Okay? So, a very important and interesting topic, like I mentioned before, is protecting particularly sensitive data such as credentials. And there are many relevant types of credentials, but one of the most super common is passwords. And so let's focus on passwords for a little bit, password databases, right? And a huge number of attacks tend to target and successfully get password databases. Like one of the big ones was an incident, MySpace incident, where about 360 million accounts worth of passwords were leaked. And these were, for example, the SHA-1 hashes of the first 10 characters of the password converted to lowercase and stored without salt. And so we'll get into what that means, but in a minute. But this is a hopelessly insecure password database that is very easy for attackers to exploit. So okay, so let's go back to the three-tier architecture, to understand how this works, how passwords databases are often protected and how they can be breached. So if a user has an account on the site, they've got to be able to create an account and then later come back, enter the password, and get back into the account. In order to do that, there has to be a password database of some kind. It has to be accessible online, at least indirectly. And again, this three-level model typically works, where the user's web browser, the user enters something into the login form that gets sent to the application logic tier, which in turn puts that into a query into the password database and gets a looks up the username and the password in the database, checks whether the passwords match, and says yes, that's you, or no, that's not you, right? So this is the and if we do nothing, then with no protection, we could just, what's the simplest option? Well, we could just store the raw clear text passwords in the database, right? So that would be the simple, obvious solution. That's, really bad idea, and we realized very, very long ago that was a bad idea. The passwords are highly sensitive. Many users often use the same passwords for different accounts. So anybody who sees a user's password on, breaks into sees a user's email address and password in this cracked database, one of the first things they're going to do is try that password on Yahoo and Google and this, that, and the other online service. Try it everywhere. See where else, on the internet the user happens to be using that same email address and password. And for a lot of users and a lot of passwords, that's going to work. The attacker will find other accounts that the user happens to be using the same password on, right? And so, it's obviously bad just to have a database expose all the passwords in clear text to any hacker that might get a copy of the database. So what do we do? Well, the solution we came up with long ago, that's a terrible solution, but it's a starting point to slightly less terrible solutions at least, is just to hash the password. Right? Use a preferably cryptographic hash function. MD5 used to be the standard one of choice. MD5 is now considered cryptographically broken. So definitely don't use it anymore for this, but this used to be fairly common. So So you would just take a password, run it through this hash function, and you get, a big random-looking string out. Now, what's the problem? Well, there are at least 3 problems. First of all, it's vulnerable to brute force attacks. If I just, have use a lot of compute power to try all of the, 4, 5, 6-digit passwords, run all of the possible strings through, through this hash function, for some range of possible strings, I can, I can find the matching hash that matches the hash stored in this password database that I ran away with, or that I came across, right? So, and with the computational power that's cheap these days, not only with standard machines, but things like GPUs and FPGAs can run, execute SHA-1, MD hash functions like MD5, SHA-1, SHA-256, can try enormous numbers, try potential password brute force attacks at insane rates, basically. And so any kind of weak password, short or otherwise weak, is easy to detect this way. Then there's dictionary attacks. So even if you a lot of passwords are already known to be used. Hackers have, kind of enormous databases of passwords that users have been known to use, here and there, and that's just a really big dictionary. And so the first thing you're going to do when you find a new database is try all of the old passwords from, from this old collection of this old database, and see what hits. And again, if you're trying to crack a good-sized password database, you'll probably find some users that are using the same password, happen to be using the same password that's already in the dictionary, right? And then you can make these types of attacks more efficient using interesting techniques called such as rainbow tables, which I'll talk about in a minute. So let's first just take a quick look at brute force attacks. So with modern GPUs, general purpose GPUs, like I mentioned, we can run hash functions like SHA-256 at ridiculous rates. For example, 8.2 billion password combinations per second. This was at least a couple of years ago when we first created these slides. I'm sure this number is already much bigger than 8.2. One pen tester not long ago cracked 13,000 passwords from a database in 1 hour out of the total of 16,000 passwords in the database. So just using brute force and state-of-the-art dictionary and brute force attacks, he was able to crack the vast majority of passwords in a real password database that was stolen, right? So in one of the other recent cards, GPU cards, managed to try about 1 trillion combinations in 2 minutes. So, basically this is just to try to illustrate the effectiveness of brute force attacks, these, using today's hardware against, especially against naive approaches for protecting passwords or anything else. And this literally, this is not specific to passwords. If you hash anything, run anything remotely privacy sensitive through a cryptographic hash and think that's secure and unreversible, you're probably wrong if the thing you ran into it is at all, it has limited entropy, is too short, and potentially guessable, potentially in a dictionary anywhere that an attacker might collect, right? So a hash function is only one way, to the extent that what goes in it is high entropy and not guessable and not in a dictionary anywhere, right? And that's a really critical thing to keep in mind. Otherwise, if those properties don't hold, then a hash function is not one way. You can get back to what went in. And of course, there are many techniques to optimize these kinds of searches. Like, hackers know that people like to change 1s into L's and E's into 3s and stuff like that, and they'll try all those variations. Changing an easily a simple password into a harder to guess password using these kind of transformations, that doesn't work anymore. It adds very, very little additional entropy these days against brute force attacks. A little, but not much. So I mentioned rainbow tables briefly. So what are rainbow tables? So rainbow tables. So the problem with using dictionary attacks, dictionary attacks are super effective if you can store an enormous dictionary of clear text passwords associated with the hash, right? So if you have an enormous table of every password that you've seen in a bunch of existing dumps online, and/or possible passwords that you've just computed yourself just by brute forcing every password up to n characters long, right? You can build an enormous table of clear text hash combinations. But that takes a lot of storage, right? And rainbow tables are a very nice way to reduce that storage cost. So basically a way to crack passwords using dictionaries while reducing the amount of storage, the amount of disk you need basically to hold that giant table from order n, where n is the number of passwords in the table, down to order square root of n, basically cutting the number of bits in half. So this is asymptotically really a huge reduction in the amount of storage you need to actually use a dictionary-based attack against passwords. So how does a rainbow table, what does it work? How does it work? So the basic idea, let's see. The basic idea, a rainbow table is basically a big table of chains. Each row starts from some kind of seed, which might just be pseudo-random or pseudo-random. We pick a random number or pseudo-random number for each row, and then we hash it. And then we go through a reduction step I'll get into in a minute. We hash it again, reduce, hash, reduce, and so on. And at each step, we're basically generating a new password try and then rehashing it, and then generating another potential password and then rehashing it again. We're trying a bunch of combinations in each row, and each row is going to be about order square root of n in length. And then we're going to have about square root of n different rows that are basically independent of each other. And so as you can see, there are a total of about n separate password cells in the whole table, but we're only going to have to store the last row, the last column in each row, maybe the first column, the seeds as well, but those can typically be regenerated algorithmically. So we basically only need to store the very last column, the last hash in each row, so the last column, and that's the entire thing we store in order to crack, which is order square root of n in size, and we can store that to crack, to brute force n possible password tries. So let's drill down a little bit into what's in each of these rows. Well, each of these rows we start with some big random seed that can be as big as we want, but then we just truncate it. We cut off the beginning, and we reduce that into a potential password. And this we can reduce it. We can also reduce it based on the set of and frequencies of characters that we want to search for as well. But we'll ignore those kinds of steps now. But basically, we go through a reduction function that reduces it to only a member of the password search space we want to actually find, and then we take that and hash it and then reduce it again to form another potential password in that big search space, and so on. So we're just basically, within each row, we're using these progressive hashes to just bounce around the search space pseudo-randomly, finding different potential passwords and what they hash to, right? Password, what it hashes to, password, what it hashes to, and so on, right? But we're not going to store all of those. Instead, we're going to do a bunch of those things and then just store the one hash at the end of each row, okay? Now, how do I use that? Yeah.
So what happens if my password actually has like a dot?
Yeah. Yeah, so that's where the kind of the character, I ignored the character set issues. So if we interpret that as a hex version of the password, right, then and we're searching for all possible ASCII and non-ASCII characters in the password, I will eventually hit the dot character, as what is the ASCII code for dot? I can't remember, 42. So if those are basically hex bytes, then I will hit the dot character. That will be in the space. But I might be doing a pretty wasteful search because I'll be searching for characters like the unprintable characters from 0 to 31 and the characters above 127 that probably are illegal to characters for passwords anyway. So in practice, to optimize that, you want to change that reduce function so that it only produces valid password characters, and you probably want to scope the distribution as well. So this is where you can include rules like, well, certain characters are more common than other characters in passwords. Well, we can make that a bigger part of the space and other characters are small. Right? So there's a bunch of kind of statistical optimization techniques that you can embed in that reduce function to optimize it for types of passwords that are both valid and more or less common. But that's all optimization tweaking stuff. So if you just produce ASCII, every possible ASCII character up to some target length, you'll eventually find it. Find all the passwords in that space. It just might be less efficient. Okay. Yeah. Good question. So we built these rainbow tables, these big long lists of rows, and we've stored only the final hash in each row. But we've gotten a password database that we want to crack. We have a particular password we want to crack using this rainbow table. How do we find it? Well, if we just look for check the hash against the hashes that we've stored, we'll only hit if it happens to be, if we get really lucky and we hit kind of the last column, which is very unlikely. It's a 1 in square root of n chance. That wouldn't be very effective. But we don't have to do that. What we do is we take the hash of the password that we want to crack, and then we run it through the reduce function, and then hash it, and then we behave like we are creating a new row starting from the unknown, the hash of the unknown password, build a whole potentially square root of n size row. But at each step, we reduce hash. We look up to see each of the hashes we encountered. Is that hash in this last column of the database anywhere? So for each of the hashes we produce from the password, we look that up to see if it's in one of the square root of n final hashes of the column, right? And so, if you think about it, as long as you do this square root of n times, test up to square root of n hashes, produce the equivalent of a complete row starting with the unknown password hash. If that's anywhere in the database, you will have at least identified the row it's in. Right? So one of those hashes will be the last that you produce, will be the last hash in some row of the database. And then you know the row, and then you go back to the seed of that row, and you regenerate that whole row from the beginning to get until you get the password that hashes to the original thing. So you just kind of go in a circle using that row, right? And so basically that requires only square root of n hashes, to crack one password rather than order n. Yeah.
But for that, you have to know exactly the size of the password, because if we
Yep, absolutely. So this only works for a well-defined search space. Let's say you have to decide, I'm going to build a rainbow table covering that tries to cover all of the passwords up to 7 characters in size from this particular subset of the ASCII space or something, right? So you define the search space. You have to predefine the search space, and this reduce function has to be a function that transforms an arbitrary hash into a appropriately distributed sample from that search space that you decided on, right? And once you do that, you will and then another important thing to understand is because this rainbow table is kind of probabilistically jumping around randomly in the search space, you'll only you won't ever get an absolute guarantee that you will actually hit every possible password in the rainbow table. But if you make the rainbow table a bit larger than and a bit means logarithmic. You make in practice you just add a multiply in an additional logarithmic factor. Make the if the total password search space you want to hit completely is size n, you make the rainbow table size n log n in total. And with the statistical properties, you'll get a high probability guarantee that you will hit every single password with high probability. And that there's a bunch of statistical details, but multiplying in another log n term to hit every possible password doesn't add that much size to the table. But then maybe you don't need an absolute guarantee too. Most hackers, are pretty much fine if I manage to hack, 13,000 out of the 16,000 passwords. Yeah, that's a pretty good result, right? Yeah.
Do we have to use the same hash function that the one used for the password?
Yes, absolutely. So the hash function. So this step from the password to the hash has to be the same hash function that's used in the password databases we're cracking. So that part has to be aligned with the password database. But usually that's a well-known hash function. It's SHA-1 or MD5 or SHA-256, and you just build a rainbow table for one of the for each of the hash functions you care about, right? Yeah. So another interesting little detail, because this reduce function is reducing this big high entropy hash into a small, fairly small low entropy hash. This actually, in a high entropy hash, has some probability of collisions, but we generally consider that a negligible probability. When we reduce it down to a small password, the probability of collisions becomes non-negligible, right? And so if we build these rows in the more or less naive fashion of just basically using the same hash and the same reducer at each step, if we do get a collision, we can get into cycles where we got to there, we get we produce something, and then that event eventually leads us around to the same thing, and then basically that row the rest of that row becomes useless in terms of exploring the search space further, right? So this is a potential issue. Fortunately, there's a fairly easy trick to solve that. We basically just tweak the reduction function, right? Because the reduction function is anything we want. We just arrange for the reduction function to be slightly different for each column of the database, right? and I won't get in the details, but that just ensures that if we get unlucky at one point in a particular row, we won't get in a cycle. Even if we do produce the same password as we saw before in the same row, well, the next time we'll be using a different reduction function and we'll be jumping to a different part of the search space. All right. So okay, so that's rainbow tables. For what it's worth. Just backing up to the big picture again, rainbow tables are just an optimization of, brute force dictionary attacks where we, compute a huge dictionary of hashes and and clear text that hash to them. But it can be very effective. So in general, simple hashing is, for all these many reasons, completely inadequate these days for protecting passwords or any low entropy source of information. And so now let's look at some of the less completely broken approaches, such as adding salt, using different types of password hashing functions, and using key-based functions. So let's first look at the, by now, absolutely standard practice of just adding a salt. Right? So what is a salt? Well, a salt is just a non-secret thing, something that we store in the password database. When we use a salted password database, we don't just store the hash of the password, but we first pick a random number, say 1, 2, 3, 4, 5. Pretend that's a random number. Could happen. Right? So we pick a random number. We call that the salt for this particular password. We store the salt and the hash of the password with the salt in the database, right? So the salt changes, adds entropy to what gets hashed, right? Now, the salt is not secret to the, if the attacker gets the database, the attacker is going to get all the salts along with all the hashes of the passwords in the salt, right? So has this helped? The attacker, has all the same information as they did before, right? Well, it does help because if we use different salts for every row, if we use salt like we're supposed to, every time we set a password or create a new entry, we pick a new fresh random number, an attacker won't be able to use a simple, plain brute force attack on the hash function anymore, like a table of just all of the six character passwords and what they hash to won't work anymore because all of the passwords have a salt going into the password as well, and so as long as that's a reasonably good sized random number, that will ensure that the attacker can't just look up something independent of the salt. If the attacker wants to use brute force, they can still use brute force, but they have to brute force one entry in the password table at once, right? So, and I can create a rainbow table, but that rainbow table will only apply to one particular salt value, right?
How is that still vulnerable to dictionary attacks? Because
You have to construct a dictionary for that salt, right?
Yes. It's still vulnerable to both brute force and dictionary attacks that just search through a large space of possible passwords against this particular password entry, right? The attacker loses the ability to do a brute force attack in which the inner loop is try a potential password, get out a hash, see if that hash is anywhere in the database, right? That attack is no longer possible. That's good. The salt succeeded in making it harder. But the brute force attack where the attacker says, okay, I'm picking this particular database, password database entry with this particular salt that I want to crack, I'm just going to repeatedly try this large dictionary or large search space with that particular salt, and the password happens to be weak, that attack will still succeed, right? It will be, so dictionary or the efficiency of dictionary and brute force attacks basically get divided by the number of entries in the password database, which is good. If there's 10,000 entries in the password database, the attacker has to spend 10,000 times the CPU time, or in a brute force attack against the complete password database, because he's got to attack each password entry one at a time with a full-scale brute force attack, rather than attacking the whole database as a whole together in one brute force attack. So that's really good. Salted hashes are way better than unsalted password hashes, which is why no password database anywhere anymore should be unsalted. Should be using unsalted passwords, right? If you see an unsalted password database anywhere, somebody should be fired probably. And their benefit, because they don't change user experience, they don't add significant complexity, and so they do help, but they're not perfect. They don't completely eliminate brute force and other attacks. They just make it somewhat harder, right? Okay, so there's other approaches, other improvements that can be made, especially recently in the past number of years. There's been various efforts to build hash functions specifically for hashing passwords, or for hashing things like sensitive data like this. And typically the idea here is to make each hash function much more computationally expensive, right? Just deliberately slow down the computation of the hash function. The simplest, most naive way to do this is just to hash the password, and then hash the hash, and then hash the hash of the hash, and then hash, all the way, iterate that 10,000 times or something, right? That takes 10,000 times more, compute effort than just hashing the thing once, right? If the hash function is strong, and if the hash function is strong, then iterating the hash basically has to be done serially. You can't really parallelize that unless the crypto is broken. And so, that will slow you down. And so that can make, and of course, hashing something 10,000 times is still something on a modern CPU, that'll still take just a fraction of a second to do. So hopefully the user won't notice, it won't slow it down a valid user login significantly, because that amount of time was pretty much negligible anyway. But if an attacker gets a copy of the password database and tries to use a brute force attack, that will slow the attacker down to 10 by a factor of 10,000, right? And so that's, again, not a perfect solution, but it's good. Any way we can slow down an attacker who potentially gets a database by some significant factor, that's good. So yet another approach is to use what we call a memory hard hash function. The problem with just iterating, or one of the problems with just iterating, is that an attacker with the right kind of hardware, such as GPU hardware or even custom hardware, such as Bitcoin mining hardware. This is the ultimate, if your password database is using SHA-256, then Bitcoin mining hardware is like the state-of-the-art in computing the number of SHA-256 hashes per second, right? So an attacker with the right kind of hardware can get huge power and efficiency advantages, or just iterating a small hash function, whereas Whereas if you incorporate the use of memories, so a memory hard hash function basically deliberately uses a megabyte of memory, or some significant chunk of memory, produces a bunch of pseudo-random stuff into all that memory, and then requires a bunch of pseudo-random random accesses to it, and mixes all of that kind of stuff together, to try to make sure that that whoever is computing this thing really has to have that much memory, and it would be difficult to get away without using that memory, right? And then it, in the end, just produces another hash, but it produces a hash that required a significant amount of memory. Now, why is that an improvement? Why do we want memory hardness? Yeah.
Because we need custom hardware and the new craft is expensive.
Exactly. So using pure computation, specialized hardware is hugely effective at optimizing pure computation. An ASIC that does SHA-256 is like millions, maybe billions of times more efficient than the same thing in general purpose CPU. But anything memory hard, so the DRAM that's in everybody's normal machines is not that different from a performance perspective from the most specialized DRAM anybody has come up with. Very small factor difference, right? So you can't get much better DRAM performance from building building DRAM into an ASIC. The DRAM you can put in an ASIC is pretty much the same DRAM as the DRAM that goes into laptops, right, in terms of performance characteristics. So the attacker loses a lot of potential advantage if we have a memory hard aspect, right? Okay, so finally we can use the even better approach in principle is to use keyed hash functions. So we'd rather be in a situation where if the attacker steals the database, they don't actually get everything that they need to crack it. So if we actually key the hash functions, and there's many ways to do this, and then hopefully store the key elsewhere, do something with the key. As long as if the attacker gets the database but not the key, then there's then that's a pretty successful defense. The attacker can't actually even run the hashes anymore without the key, right? And so that in principle makes the database uncrackable. So that's great. But of course that brings us back to the same key management challenge that we talked about earlier with full disk encryption and other things. Where do you store the key? How likely is it that the hacker can get the key along with the database, right? And so since I'm running out of time, I won't really get into that a lot. Just storing it on the same server, well, you didn't really achieve much. So you'd rather store it on a different server or a dedicated hardware security model or other devices. And so that's increasingly standard practice. So kind of running out of time. Yeah, so just in terms of to emphasize one of the issues we talked about before, side channels. We referred to timing side channels where database queries can leak information through side channels. Well, password tests. The code that tests a password or a password hash when a user logs in can also be vulnerable to side channels. For example, if you compare the newly hashed password against the hash, even the salted hash in the password database, one character at a time from left to right, really bad idea, because the length of time it takes to decide that the password is invalid depends on how far through the password you got, right? And so the attacker is going to submit queries, trying any password starting with A, any password starting with B, and so on, and notice that one of those queries took just a tiny bit longer than all the others. Got the first letter. Now let's go for the second, right? And so that reduces that one tiny side channel, reduces the exponential search space to a linear time search space. Okay, so yeah, so beware of side channels. Use constant time methods, and so also encrypt your databases. But we'll get to encrypted database processing later in the course, so we can skip that for now. So thank you. So see you next week.